Hi everyone, welcome to the chapter TCP Communication Process. In the first point is TCP Server Process. You already know the fundamentals of TCP. Understanding the role of port number will help you to grasp the details of the TCP communication process. In this topic, you will also learn about TCP three-way handshake and session termination process. Each application process running on a server is configured to use a port number. The port number is either automatically assigned or configured manually by a system administrator. An individual server cannot have two services assigned to the same port number within the same transport layer service. For example, a host running a web server application and a file transfer application cannot have both configured to use the same port, such as TCP port 80. An active server application assigned to a specific port is considered open, which means that the transport layer accepts and process segment address to that port. Any incoming client request address to the correct socket is accepted, and the data is passed to the server application. There can be many ports open simultaneously on a server, one for each active server application. And select each tab for more information about TCP server process. In the first step is client sending TCP request. Client 1 is requesting web service and client 2 is requesting email service for the same server of the same server, sorry. Client 1, client 2, HTTP request, SMTP request, source port, destination port. Okay. The next step is request destination ports. Client 1 is requesting web service using well-known destination port 80 HTTP, and client 2 is requesting email service using well-known port 25 SMTP. Okay. The next step is request source port. Client requests dynamic call generate a source port number. In this case, client 1 is using source port 49, 150, 152, and client 2 is using source port 51, 152. Okay. And the next step is response destination ports. When the server responds to the client request, it receives the destination and source port of the initial request. Notice that the server response to the web request now has destination port 49152 and the email response now has destination port 51152. Okay. Server response to TCP client use the source port from the request packet as the destination port. And the last step is response source port. The source port in the server response in the original destination port in the initial request. Okay. The next topic or point is TCP Connection Establishment. In some cultures, when two persons meet, they often greet each other by shaking hands. Both parties understand the act of shaking hands as a signal of a friendly greeting. Connection on the network are similar. In TCP connection, the host client establishes the connection with the server using the three-way handshake process. In the first step is sync. The initial client requests a client-to-server communication session with the server. Okay, sending sync. Step 1, sec 100. Okay, the next step is ACK and sync. The server acknowledges the client-to-server communication session and requests a server-to-client communication session. Okay. B send ACK response and sync request to A. And the step 3 is ACK. The initiating client acknowledges the server-to-client communication session. Establish. The three-way handshake validates that the destination host is available to communicate. In this example, host A has indicated that host B is available. Session termination. To close a connection, the finish fin control flag must be set in the segment header. To end each one-way TCP session, a two-way handshake consisting of a fin segment and an acknowledge ACK segment is used therefore to terminate a single conversation supported by TCP. For exchange are need to end both sessions. Either the client or the server can initiate the termination. In the example, the term client and server are used as a reference for simplicity, but any two hosts that have an open session can initiate the termination process. Mm, In step 1 is fine or fin. When the client has not more data to send in the stream, it sends a segment with the fin flag set. Step 2 ACK. The server sends an ACK to acknowledge the receipt of the fin to terminate the session from the client to server. Step 3 fin. The server sends a fin to the client to terminate the server to client session. And step 4 ACK, the client responds with an ACK acknowledge the fin from the server. When all segments have been acknowledged, the session is closed. The next point is TCP three-way handshake analysis. Hosts maintain a state, track each data segment within a session, and exchange information about what data it received using the information in the TCP header. TCP is a full duplex protocol where each connection represents two one-way communication sessions. To establish the connection, the host performs a three-way handshake, and shown in the figure, control bit in the TCP header indicate the progress and status of the connection. These are the functions of three-way handshake. The first point is it establishes that the destination device is present on the network. The next point is it verifies that the destination device has an active service and is accepting requests on the destination port number that the initiate client intends to use. And the last point is it informs the destination device that the source client intends to establish a communication session on that port number. After the communication is complete, the sessions are closed and the connection is terminated. The connection and session mechanisms enable TCP reliability function. Control bit fields, source port, destination port, sequence number, acknowledge number, header length, reserve, control bits, window, checksum, urgent, and option, and the last is application layer data. The 6 bit in the control bit field of the TCP segment header are also known as a flag. A flag is a bit that is sent to either on or off. The 6 control bit flags are as follows: URG, urgent pointer field significant; ACK, acknowledgement flag using a connection establishment and session termination; PSH, push function; RST, reset the connection when an error or timeout occurs; SYNC, synchronize sequence number using a connection establishment; FIN, no more data from sender and using a session termination. Search the internet to learn more about the PSH and URL flags. Okay. Finish with check your understanding which of the following would be valid source and destination port for a host connection to an email server. Okay. In a mail server, the destination port is the well-known port for simple mail transfer protocol. which is 25. This is the port that the mail server will be listening on. The source port is dynamically selected by the requesting client and can be 49.152. Which control bit flags are used during the three-way handshake? That is sync and ACK. The three-way handshake consists of a three-message exchange between the following control bit flag: sync, ACK, and ACK. How many exchanges are needed to end both sessions between two hosts? 4 exchanges. 3 or 4 exchanges. Repeat. There are 4 exchanges to end both sessions between two hosts. 1. Host A send a fin. 2. Host B send an ACK. 3. Host B send a fin. 4. Host A send an ACK. And the next topic in this chapter is reliability and flow control. TCP reliability, guarantee, and oriented delivery. The reason that TCP is a better protocol for some applications is because, unlike UDP, it resends dropped packets and number of packets to indicate their proper order before delivery. TCP can also help maintain the flow of packets so that devices do not become overloaded. This topic covers these features of TCP in detail. There may be times when TCP segments do not arrive at their destination. Other times, the TCP segment may arrive out of order. For the original message to be understood by the recipient, all the data must be received and the data in this segment must be reassembled into the original order. Sequence numbers are assigned in the header of each packet to achieve this goal. The sequence number represents the first data bit of the TCP segment. During session setup, an initial sequence number ISN is set. This ISN represents the starting value of the bytes that are transmitted to the receiving application. As data is transmitting during the session, the sequence number is incremented by the number of bytes that have been transmitted. This data byte tracking enables each segment to be uniquely identified and acknowledged. Missing segments can be then by identified. The ISN does not mean at one but is effectively a random number. This is to prevent certain types of malicious attacks. For simplicity, we will use an ISN of a 1 for the example in this model. Segment sequence number indicate how the reassemble and reorder received segment, as shown in the figure. Okay, this part is very important. During session setup, an ECL sequence number is set. The ISN represents the starting value of the bytes that are transmitted to the receiving application. As data is transmitting during the session, the sequence number is incremented by the number of bytes that have been transmitted. This data backtracking enables each segment to be uniquely identified and acknowledged. Missing segments can then be identified. For security, the ISN does not begin at 1 but is effectively a random number. This is to prevent certain types of malicious attacks. For simplicity, we will use a ISN of 1 for the example in this model. Okay, TCP segments are reordered at the destination. Okay, different segments may take different routes. In the first point is data is divided into segments. Segment 1, segment 2, segment 3, segment 4. Having taken different routes, To the destination segment arrive out of order. TCP reorder the segment to the original order. Okay, segment 1, segment 2, segment 6, segment 5, segment 4, and segment 3. And reorder the segment. Okay. The receiving TCP process plays the data from a segment into a receiving buffer. Segments are then placed in the proper sequence order and passed to the application layer when reassembled. Any segment that arrive with sequence numbers that are out of order are held for later processing. Then, when the segment with the missing bytes arrive, the segments are processed in order. Okay. One of the functions of TCP is to ensure that each segment reaches its destination. The TCP servers on the destination host acknowledge the data that had been received by the source application. TCP reliability, data loss, and retransmission. No matter how well designed a network is, data loss occasionally occur. TCP provides methods of managing the segment loss. Among these is a mechanism of retransmit segments for acknowledged data. The sequence number and acknowledge number are used together to confirm receipt of the bytes of the data contained in a retransmit and then the transmit segments. The sequence number identifies the first byte of data in the segment being transmitted. TCP uses the ACK number sent back to the source to indicate the next byte that the receiver expects to receive. This is called expectation acknowledge. Prior to later enhancement, TCP could only acknowledge the next byte expect. For example, in the figure using segment numbers for simplicity, host A sends segment 1 through 10 to host B. If all the segments arrive except for segment 3 and 4, host B will reply with acknowledgement specific that the next segment expand is segment 3. Host A has no idea if any other segment arrived on host or not. Host A will therefore resend segment 3 through 10. If all the resend segments are successful, segment 5 through 10 will be duplicates. This can lead to delays, congestion, and inefficiency. Okay, segment 1, 2, 3, and segment 4 are lost. Okay. Host operating system today typically employ an option TCP feature called Selective Acknowledgement (SAC), negotiated during the three-way handshake. If both hosts support SAC, the receiver can explicitly acknowledge which segment bytes were received, including any discussion segments. Discontinuous segment. The sending host will therefore only need to retransmit the missing data. For example, in the next figure again, using segment number for simplicity, host A sends segments 1 through 10 to host B. If all the segments arrive except for segment 3 and 4, host B can acknowledge that it has received segment 1 and 2 at 3, and selectively acknowledge segment 5 through 10, seg 5 to 10. Host A will only need to resend segment 3 and 4. Okay. Note: TCP typically sends ACKs for every other packet, but other factors beyond the scope of this topic may alter this behavior. TCP uses time to know how long to wait before resending a segment. In the figure, play the video and click the link to download PDF file. The video and PDF file examine TCP data loss and retransmission. Okay, the next point is TCP flow control, window size, and acknowledgement. TCP also provides mechanisms for flow control. Flow control is the amount of data that the destination can receive and process reliably. Flow control helps maintain the reliability of TCP transmission by adjusting the rate of data flow between source and destination for a given session. To accomplish this, the TCP header includes a 16-bit field called the window size. The figure shows an example of window size and acknowledgement. TCP window size example. Okay, MSS maximum segment size. Send window 10,000 during three-way handshake window size 10,000 MSS and 1416. Sequence number 1, sequence number 1461. Receive acknowledge send window sequence number. Okay. Maximum segment size. The window size determines the number of bytes that can be sent before expecting an acknowledge. The acknowledgement number is the number of the next expected byte. The window size is the number of bytes that the destination device of a TCP session can accept and process at one time. In this example, the PCB initiate window size for the TCP session is 10,000 bytes. Starting with the first byte, byte number 1, the last byte PCA can send without receiving an acknowledge is by 10,000. This is known as the send windows of PCA. The window size is included in the every TCP segment so the destination can modify the window size at any time depending on buffer availability. The initial window size is agreed upon when the TCP session is established during the three-way handshake. The source device must limit the number of bytes sent to the destination device based on the window size of the destination. Only after the source device receives an acknowledgement that the bytes have been received can it continue sending more data for the session. Typically, the destination will not wait for all the bytes for its window size to be received before replying with an acknowledgement. As the bytes are received and processed, the destination will send acknowledgement to inform the source that it can continue to send additional bytes. For example, it's typical that PCB will not wait until all 10,000 bytes have been received before sending an acknowledgement. This means PCA can adjust its send windows as it receives acknowledgement from PCB. As shown in the figure, when PCA receives an acknowledgement with the acknowledgement number 2921, which is next expected by the PCA send window will increment to 920 bytes. This changes the send windows from 10,000 bytes to 12,920 bytes. PCA can now continue to send up to another 10,000 bytes to PCB as long as this does not send more than its new sender window at 12,920. A destination sending acknowledgement as is processed by receive and the continual adjustment of the source send window is known as sliding windows. In the previous example, the send windows of PCI increments or slide over another 2921 bytes from 10,000 to 12,920. If the variability of the destination's buffer space decreases, It may reduce the window size to inform the source to reduce the number of bytes it should send without receiving an acknowledgment. Note: devices today use the sliding window protocol. The receiver typically sends an acknowledgment after every two segments it receives. The number of segments received before being acknowledged may vary. The advantage of a sliding window is that it allows the sender to continuously transmit segments as long as the receiver acknowledges previous segment. The details of a sliding window are beyond the scope of this course. The next point is TCP flow control maximum segment size MSS. Okay, this is for the next chapter. See you in the next one.